March 19th, 1945. Deep inside a reinforced hangar at Tachikawa Army Air Arsenal, 20 miles west of Tokyo, Japanese engineers stood frozen in silence before a machine that shouldn't exist. The Boeing B-29 Superfortress, tail number 4263524, designated Tramp, lay partially dismantled on the concrete floor, its aluminum skin reflecting the harsh overhead lights. What stopped them wasn't the size. Though at 99 feet long, with a wingspan stretching 141 feet, it dwarfed any Japanese bomber. What paralyzed them was the fire control system, a network of electronic computers, remote gun turrets, and interconnected sighting stations that represented technology years beyond anything in the Japanese arsenal. One engineer, a former university professor named Takeshi Yamamoto, reached out to touch the central fire control computer, his hand trembling. The device weighed more than 200 pounds, contained thousands of electronic components, and could calculate firing solutions faster than 10 human gunners working simultaneously. Japan had nothing remotely comparable. The revelation of this technological gap would cascade through Japanese military leadership over the following weeks, forcing them to confront an uncomfortable truth. They were fighting an enemy whose industrial and technological capabilities had surpassed their own by margins they hadn't imagined possible. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The story of how this particular B-29 came to rest in a Japanese hangar begins not with its capture, but with the strategic bombing campaign that brought American heavy bombers to the skies over Japan. The B-29 represented the culmination of American aviation engineering, a pressurized, high-altitude bomber designed specifically to strike targets across the vast distances of the Pacific. Development had begun in 1939 when the Army Air Corps issued specifications for a hemispheric defense weapon, an aircraft capable of reaching any target on Earth from American bases. Boeing's design featured 4 Wright R-3350 duplex Cyclone engines, each producing 2,200 horsepower. The pressurized cabin allowed the crew of 11 to operate at altitudes exceeding 30,000 feet without oxygen masks. The defensive armament included 12 50-caliber machine guns and 1 20mm cannon, all remotely operated through the revolutionary fire control system. The aircraft could carry 20,000 pounds of bombs to targets 1,500 miles away and return. No other bomber in the world matched these capabilities. Production began in 1943 at facilities across the United States. Boeing's plants in Wichita and Renton led manufacturing, supplemented by Bell Aircraft in Marietta, Georgia, and Martin Aircraft in Omaha, Nebraska. By war's end, nearly 4,000 B-29s had been built, representing one of the most expensive weapons programs of World War II. The first combat missions against Japan launched from bases in China and India in June 1944. These early raids achieved limited results due to logistical challenges, but they demonstrated that Japanese home islands now lay within reach of American strategic bombers. The capture of the Mariana Islands, specifically Saipan, Tinian and Guam in summer 1944, transformed the strategic situation. These islands lay approximately 1,500 miles south of Tokyo, placing all major Japanese cities within B-29 range from well-supplied bases. Construction battalions carved bomber bases from jungle and coral, building runways that stretched 2 miles long to accommodate the heavy aircraft. By November 1944, the 21st Bomber Command under General Haywood Hansell began sustained operations against Japanese industrial targets. Japanese defenses initially struggled to counter the high-altitude bombers. The Nakajima Ki-44 Tojo and Kawasaki Ki-61 Tony fighters represented Japan's best interceptors, but both encountered severe challenges engaging B-29s at operational altitudes above 30,000 feet. Engine performance degraded in the thin air, climb rates decreased, maneuverability suffered. Even when interceptors reached bomber altitude, the closing speed left minimal time to aim and fire before flashing past the formation. Japanese pilots reported that the Americans maintained tight formations with overlapping fields of fire that made approach from any angle suicidal. The remote-controlled turrets tracked targets smoothly, engaging multiple threats simultaneously. Pilots accustomed to manually aimed defensive guns on Japanese bombers couldn't comprehend how American gunners achieved such accuracy while the bomber maneuvered. They didn't yet understand that computers were aiming the guns, not human hands alone. The first B-29 losses over Japan came primarily from mechanical failures rather than combat damage. The right engines, pushed to their limits to achieve the required performance, proved temperamental. Overheating, particularly in the rear row of cylinders, caused fires. Magnesium engine components that saved weight became ignition sources when temperatures exceeded design limits. Crews flying from the Marianas faced 7 hours over open ocean, just reaching Japan, 7 more returning. Any mechanical problem during this 14-hour mission could prove fatal. Several B-29s ditched in the Pacific when engines failed. Others limped back to Iwo Jima after that island's capture in March 1945 provided an emergency landing field halfway between the Marianas and Japan. Some didn't make it at all, disappearing without trace into the vast emptiness of the Pacific. These mechanical vulnerabilities represented the price of pushing aviation technology to its absolute limits. The B-29 required performance levels that strained metallurgy, engine design, and systems integration beyond anything previously attempted. Japanese intelligence services desperately needed detailed information about these bombers. Photographs from distant reconnaissance flights revealed external dimensions and general configuration, but provided no insight into systems, capabilities, or vulnerabilities. Interrogations of captured American aircrew yielded limited technical intelligence. Bomber crews knew how to operate their aircraft but typically lacked engineering knowledge of underlying systems. They could describe procedures for operating the fire control system but couldn't explain the analog computers that made it function. They knew the pressurization system maintained cabin pressure equivalent to 8,000 feet while flying at 30,000 feet altitude, but couldn't detail the compressors and regulators that accomplished this. Japanese intelligence officers needed physical access to an intact B-29 to truly understand what they faced. Several bombers damaged over Japan had crash-landed on the home islands during early raids. However, these aircraft typically burned after crashing, and impacts destroyed sensitive equipment. Pieces could be recovered, but reconstructing complete systems from wreckage proved impossible. The breakthrough came on November 24, 1944, during the first major raid against Tokyo. 111 B-29s from the 73rd Bombardment Wing launched from Saipan, targeting the Nakajima Aircraft Company's Musashino engine plant in western Tokyo. The raid encountered heavy clouds obscuring the target area. Only 24 bombers dropped on the primary target. Results were poor, with minimal damage to the factory. Several aircraft sustained damage from anti-aircraft fire and fighter attacks during the raid. One B-29, struck by fragments from a phosphorus bomb dropped by a Japanese fighter attempting to ignite the bomber, suffered damage to 2 engines. The phosphorus scattered across the wing, burning through aluminum skin and damaging control cables. The pilot, Captain Howard Jarrell, struggled to maintain control as the aircraft lost altitude. The crew jettisoned bombs and all removable equipment to reduce weight. They threw out ammunition boxes, tools, oxygen bottles, anything not absolutely essential. The lightened bomber limped southward, trailing smoke from the burning wing. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. Jarrell realized they couldn't reach Saipan. The damaged engines couldn't maintain altitude for the 7-hour flight over open ocean. He considered ditching near one of the American submarines stationed along the route for air-sea rescue, but the violent ditching would likely kill crew members. Instead, he spotted what appeared to be an island ahead, partially obscured by clouds. Navigation charts identified it as one of the Bonin Islands, a small volcanic archipelago roughly halfway between Tokyo and the Marianas. The island of Chichijima offered a small Japanese naval base, which meant enemy territory, but at least they'd survive the landing. Jarrell ordered the crew to prepare for crash landing. They'd become prisoners, but prisoners could survive the war. The alternative was drowning in the Pacific. The B-29 descended through clouds, breaking into clear air 500 feet above the ocean. Jarrell spotted Chichijima ahead, the volcanic island rising steeply from the sea. No suitable landing area existed. The island was too small, too mountainous. He'd have to ditch offshore and hope the crew could reach land before the aircraft sank. At 3:15 in the afternoon, the B-29 hit the water approximately 1 mile offshore from Chichijima. The impact tore away the nose section. Water flooded the forward fuselage instantly. The aircraft remained afloat for 90 seconds, long enough for most of the crew to escape through emergency hatches. Japanese naval personnel on the island observed the crash and dispatched boats. They recovered 9 crew members from the water. 2 men had died in the initial impact. The recovered aircraft, though damaged by the crash, remained substantially intact below the waterline. Japanese salvage teams worked for 3 weeks to raise the bomber from 30 feet of water. They fabricated pontoons, attached cables, and slowly lifted the fuselage until it broke the surface. The salvage effort represented a massive undertaking, but Japanese Naval Command considered the potential intelligence value worth any cost. Once raised, they towed the waterlogged aircraft to shore. Engineers drained the fuselage, carefully documenting every component and system. The forward section had been destroyed by impact, and salt water had corroded many systems, but the majority of the aircraft remained intact enough for detailed study. In December 1944, the salvaged B-29 was transported by barge to the mainland. The journey required careful planning, as the bomber was too large to fit on any single transport vessel. Engineers partially disassembled the aircraft, removing wings and stabilizers. These were loaded onto barges along with the fuselage and transported to Yokosuka Naval Base. From there, everything was moved by rail to Tachikawa Army Air Arsenal, where Japan's premier aviation engineers waited to begin their examination. The arsenal, located in a western suburb of Tokyo, served as the primary research and development facility for the Japanese Army Air Force. It housed wind tunnels, test facilities, and workshops staffed by the nation's top aeronautical engineers. Many held advanced degrees from Japanese universities or had studied abroad before the war. They represented the intellectual elite of Japanese aviation, men who understood engineering principles and could recognize sophisticated technology when they encountered it. The reassembly process took weeks. Engineers carefully positioned the fuselage on support stands, reattached wings and stabilizers, and reconnected severed cables and hydraulic lines to understand the routing. They weren't attempting to make the aircraft airworthy, but rather to reconstruct systems sufficiently to comprehend their function. Hundreds of photographs documented every step. Technical artists created detailed drawings. Everything was measured, weighed, and recorded. The initial examination focused on overall layout and design philosophy. Japanese engineers immediately recognized that American designers had solved problems differently than their Japanese counterparts. Where Japanese aircraft typically featured lightweight construction with minimal redundancy to maximize performance, the B-29 incorporated backup systems throughout. Dual hydraulic systems ensured that damage to one wouldn't cripple flight controls. Multiple fuel tanks with cross-feed capabilities allowed continued operation even after several tanks were holed. The electrical system featured redundant generators and battery backup. Every critical system had an alternate. This design philosophy reflected different national priorities. Japanese engineers, working under severe resource constraints, designed aircraft that were as light and simple as possible. Every kilogram saved meant increased range or payload. Every component eliminated meant lower manufacturing cost and reduced maintenance requirements. American engineers, working with abundant resources, prioritized reliability and survivability over absolute efficiency. The pressurization system astounded the Japanese engineers. The entire crew compartment, from the nose through the bomb bay to the rear gunner station, maintained cabin pressure at high altitude. This allowed the crew to operate without bulky oxygen masks and heavy flight suits. They worked in shirt sleeves at 30,000 feet where outside temperatures dropped to 40 below zero. The system used engine-driven compressors to force air into the sealed cabin. Regulators maintained the desired pressure differential between inside and outside. Outflow valves controlled the rate of pressure change during climbs and descents. Seals at every hatch, window, and penetration prevented leaks. The engineering required to maintain pressure while the aircraft maneuvered, while bomb bay doors opened and closed, while temperatures fluctuated from ground-level heat to stratospheric cold, represented a systems integration challenge that Japanese engineers had never attempted. Japan had experimented with pressurized aircraft, but nothing operational existed. The closest equivalent was the Tachikawa Ki-77, an experimental high-altitude bomber that never entered production. That aircraft featured a pressure cabin for the three-man crew, but the system proved unreliable and added so much weight that performance suffered. Japanese engineers had concluded that pressurization wasn't worth the complexity for their purposes. Examining the B-29 system revealed how wrong that assessment had been. The Americans had solved every technical challenge. The seals didn't leak. The compressors operated reliably. The structure withstood pressure differentials that would have torn apart Japanese designs. Most impressively, the entire system was maintainable. Japanese engineers examining maintenance documentation discovered that ground crews could service the pressurization system with standard tools. Components were designed for replacement rather than repair. If a compressor failed, mechanics unbolted it and installed a replacement. This approach required manufacturing spare components in quantity, something Japan's limited industrial base couldn't support, but it meant that American bombers spent less time grounded for maintenance. A Japanese bomber with a complex system failure might require days or weeks of repairs by skilled technicians. An American bomber with the same failure could be fixed in hours by relatively unskilled mechanics swapping components. The four Wright R-3350 engines, each a massive 18-cylinder radial producing over 2,000 horsepower, represented engineering far beyond current Japanese capabilities. The largest Japanese bomber engine, the Nakajima Ha-45, powering the Nakajima G-8N Rita, produced only 1,900 horsepower. The American engines were larger, more powerful, and more complex. They featured two-stage superchargers to maintain power at high altitude. Sophisticated cooling systems managed heat from cylinders producing tremendous power in thin air. Fuel injection precisely metered gasoline flow under varying conditions of altitude, temperature, and power setting. Japanese engineers completely disassembled one engine, laying out thousands of components across workshop floors. They measured tolerances, analyzed metallurgy, and studied manufacturing techniques. The precision machining exceeded anything in Japanese production. American factories had achieved dimensional tolerances measured in thousandths of an inch across large castings. Japanese manufacturers, working with less sophisticated machine tools and facing raw material shortages, couldn't match this precision. The metallurgy revealed similar gaps. The Americans were using aluminum alloys with superior strength-to-weight ratios. Steel components in high-stress areas featured alloys that combined hardness with toughness, resisting both wear and fracture. Magnesium components saved weight while maintaining structural integrity. Every material had been optimized for its specific application. Japanese metallurgists examining these materials understood the chemistry but lacked the industrial capacity to manufacture such alloys in the quantities required for mass production. Knowledge didn't equal capability. Understanding how Americans achieved superior performance didn't give Japan the resources or industrial infrastructure to duplicate it. The remote-controlled defensive armament system, however, represented the greatest shock. This was the technology that would haunt Japanese fighter pilots and obsess Japanese engineers for months. Instead of individual gunners manning stations at each turret as in Japanese bombers, the B-29 featured 5 gunners operating all defensive weapons through remote sighting stations. The system worked through analog computers, mechanical devices that calculated firing solutions based on inputs from the sighting stations. When a gunner tracked a target through his sight, the computer received continuous data about target position, range, and angular velocity. It simultaneously received data about the bomber's altitude, airspeed, and attitude. The computer processed all of this information and calculated where the guns needed to point to hit a moving target from a moving platform. The calculations accounted for bullet trajectory, time of flight, deflection angles, and relative motion. It did this continuously, updating dozens of times per second, providing firing solutions more accurate than any human gunner could calculate manually. The system's sophistication became apparent as Japanese engineers traced circuits and studied mechanisms. The central fire control computer occupied a pressurized compartment in the fuselage. Cables connected it to 4 remote sighting stations where gunners worked and to 5 turret systems mounting the actual weapons. Each turret could be controlled by multiple gunners, allowing flexible assignment of defensive coverage. If one gunner engaged targets on the left side, another could simultaneously engage threats from the right. If a sighting station was damaged or a gunner wounded, control could be transferred instantly to a backup station. The system provided redundancy and flexibility impossible with manually aimed weapons. The upper forward turret mounted 4 50 caliber machine guns. The upper rear turret held 2 more. Each lower turret, forward and rear, carried 2 additional 50s. The tail position featured 2 50 calibers and 1 20mm cannon. Total defensive armament comprised 12 50 caliber machine guns and 1 cannon, all remotely controlled through the computer-based fire control system. The firepower concentration exceeded anything on Japanese bombers, and the accuracy was unprecedented. Japanese engineers studying the system realized it represented a fundamental paradigm shift in bomber defense. Traditional bomber defensive armament relied on human gunners physically positioned at gun stations, manually tracking targets and leading their aim to account for relative motion. This approach required enormous skill, worked poorly in combat conditions with high stress and rapid maneuvering, and left significant blind spots in defensive coverage. The American system eliminated these limitations. Gunners worked from comfortable, protected stations with excellent visibility through optical sights. They simply kept the tracking reticle on the target. The computer calculated everything else. If a fighter attacked from an angle where no direct line of sight existed from any single sighting station, multiple gunners could engage, with the computer coordinating their fire. The system could even engage targets automatically, tracking aircraft that came within range parameters even without gunner input. This level of automation in 1944 seemed almost impossible to Japanese engineers accustomed to purely mechanical systems. The analog computer itself represented technology that Japan simply didn't possess in operational form. American engineers had developed electromechanical computing devices capable of solving complex ballistic equations in real time. The computer in the B-29 used a combination of mechanical gears, cams, and electrical servos to perform calculations. Input data from the sighting stations arrived as electrical signals representing angular position. The computer converted these signals into mechanical motion, using precision-machined gears to multiply, divide, and integrate values. The output drove servos that positioned the turrets. The entire process occurred continuously, creating a closed-loop feedback system that adjusted aim even as both bomber and target maneuvered. Japanese engineers had theoretical knowledge of such systems. University professors had published papers on fire control computing before the war. However, translating theory into functioning hardware proved insurmountable. The precision manufacturing required for the gear trains exceeded Japanese industrial capabilities. The electrical components needed for reliable servo systems weren't available in sufficient quality or quantity. The systems integration knowledge necessary to make everything work together didn't exist in Japanese engineering teams. One engineer, Ichiro Tanaka, had studied electrical engineering at Tokyo Imperial University before the war. He spent 3 days examining the computer's electrical systems, tracing circuits and measuring component values. His report to superiors concluded that Japan could theoretically build such a device given unlimited resources and time. Neither was available. Manufacturing the required precision components would take years to develop. Training technicians to maintain such systems would require establishing entirely new technical schools. Even if Japan somehow produced a working prototype, Mass production would divert resources desperately needed for fighters and basic bombers. The fire control system represented a dead end for Japanese aviation, not because the technology was incomprehensible, but because the industrial and educational infrastructure necessary to implement it didn't exist. The Americans possessed not just superior engineering knowledge, but an entire ecosystem of technical education, precision manufacturing, quality control, and systems integration that Japan couldn't replicate. The optical sighting systems connected to the computer demonstrated similar sophistication. Each gunner station featured a reflector sight with variable magnification and automatic ranging. The gunner looked through the sight at the attacking fighter, centered the tracking reticle on the target, and squeezed the trigger. The sight measured angular position continuously, sending this data to the computer. A ranging mechanism, using optical triangulation or radar ranging depending on the model, provided distance information. The computer combined angular data and range to calculate a complete firing solution. Japanese engineers examining these sights recognized individual components. The optics used standard lens grinding techniques. The electrical motors driving the position encoders were conventional designs. The mechanical linkages connecting everything were beautifully engineered but not beyond Japanese understanding. However, the integration of these components into a functioning system that could operate reliably in combat conditions, at high altitude, in extreme temperatures, while subject to vibration and maneuvering loads, represented systems engineering at a level Japan hadn't achieved. The manufacturing quality throughout the aircraft impressed the Japanese engineers as much as the design sophistication. Every component showed evidence of mass production techniques that maintained tight tolerances. Aluminum sheets forming the skin were precisely formed with consistent thickness. Rivets were uniform, properly set, showing none of the irregularities common in hand-formed Japanese construction. Wiring harnesses were organized, labeled, and routed through protective conduits. Hydraulic lines featured proper support brackets at regular intervals. Everything suggested manufacturing processes under rigorous quality control, producing thousands of aircraft to consistent standards. Japanese aircraft manufacturing, by contrast, relied heavily on skilled craftsmen hand-fitting components. Each aircraft was essentially custom-built, with tolerances varying between individual machines. This approach produced excellent aircraft when skilled workers had time and materials, but it couldn't scale to the production volumes the Americans were achieving. Japan was building aircraft one at a time in workshops. America was manufacturing them by the hundreds on assembly lines. The structural design revealed another philosophical difference. The B-29's fuselage used semi-monocoque construction with longerons, stringers, and formers supporting an aluminum skin that carried primary loads. This was efficient construction, creating a lightweight yet strong structure. Japanese bombers typically used similar principles, but the American execution showed superior attention to stress analysis and damage tolerance. Engineers examining stress points around wing attachments and bomb bay openings found reinforcements precisely sized for expected loads. The structure included redundancy, with load paths that could distribute stress if primary members failed. Damage to one section wouldn't necessarily lead to catastrophic failure of the entire structure. Japanese designs, optimized for absolute minimum weight, often lacked this redundancy. A single structural failure could propagate through the airframe. The bomb bay itself demonstrated thoughtful engineering. The enormous internal space could accommodate 20,000 pounds of ordnance in various configurations. Bombs hung from hydraulically operated racks that could release individually or in sequence. The bay doors, which had to seal the pressurized fuselage yet open reliably at high altitude in freezing temperatures, used a complex linkage system that Japanese engineers found elegant. Each door segment moved on tracks, sliding backward as it opened to minimize drag. The mechanism worked smoothly despite its complexity, and redundant hydraulic systems ensured operation even if one system failed. Japanese bombers typically featured simpler bomb bay doors that hinged open, creating significant drag during the bombing run. The American sliding door design reduced drag, improved stability during bomb release, and could be opened partially for specific tactical purposes. Every detail reflected careful engineering optimization. The navigation and communication equipment revealed yet another technological gap. The B-29 carried multiple radio systems for different purposes. Long-range communication used high-frequency radios to maintain contact with bases 1,500 miles away. Shorter-range VHF radios provided aircraft-to-aircraft communication within formations. An identification friend or foe system automatically responded to radar interrogation, allowing ground controllers and other aircraft to distinguish friendly bombers from enemy aircraft. The navigation suite included a drift meter for calculating wind correction, a radio compass for homing on navigation beacons, and a radar system for navigation and bombing through clouds. Japanese engineers examining the radar installation found it particularly impressive. The APQ-13 radar, while primitive by later standards, could map terrain features from 30,000 feet, allowing navigation over featureless ocean and bombing through solid cloud cover. The system used a rotating antenna in a teardrop-shaped radome under the fuselage. The radar operator sat at a scope displaying a map-like image of the ground below. Cities appeared as bright returns, coastlines were clearly visible. The operator could identify target areas and guide the bombardier even when clouds completely obscured visual references. Japan had developed radar technology during the war, but Japanese radar systems lagged years behind American and British developments. Japanese radar operated at longer wavelengths with lower resolution, sets were heavy, unreliable, and difficult to maintain. Manufacturing quality was inconsistent, with many units failing prematurely. The microwave radar in the B-29, operating at centimeter wavelengths with resolution sufficient for navigation, represented technology that Japan simply didn't possess. Even if Japanese engineers understood the principles, they lacked the manufacturing capability to produce magnetrons, the specialized vacuum tubes that generated microwave frequencies. These tubes required precision manufacturing and exotic materials that Japanese industry couldn't supply. The communications equipment showed similar sophistication. American radios used standardized components, modular construction, and clear frequency plans that prevented interference between systems. Multiple radios operated simultaneously without interfering with each other, something Japanese communication systems struggled to achieve. The Americans had clearly devoted enormous resources to solving electromagnetic compatibility problems that Japanese engineers often didn't recognize as solvable. The crew comfort features struck Japanese engineers as almost wasteful until they considered the operational implications. The pressurized, heated cabin allowed crew members to work in comfort during missions lasting 15 or 16 hours. They could eat hot meals from heated containers. They could move between stations through pressurized tunnels without donning oxygen equipment. The pilot and co-pilot sat in comfortable seats with armrests and adjustable positioning. Every crew station had adequate lighting, ventilation, and space to perform required tasks without excessive fatigue. Japanese bomber crews, by contrast, endured missions in unpressurized aircraft, wearing heavy flight suits and oxygen masks, working in cramped positions that caused physical exhaustion. The difference in crew efficiency and effectiveness was inevitable. American crews arrived over targets relatively fresh, able to perform complex tasks with precision. Japanese crews, even on shorter missions, reached targets already fatigued from simply enduring flight conditions. The American willingness to add weight and complexity for crew comfort seemed extravagant to Japanese engineers, but the operational benefits were undeniable. The maintenance documentation accompanying the aircraft revealed another dimension of American superiority. Technical manuals detailed every system with exploded view diagrams, troubleshooting procedures, and replacement part numbers. Maintenance schedules specified inspection intervals and service requirements. Everything was standardized, documented, and designed for maintainability by relatively unskilled personnel with the aid of detailed instructions. Japanese aircraft maintenance relied heavily on experienced mechanics using knowledge passed from senior to junior technicians. Written documentation existed but was often incomplete or ambiguous. Complex repairs required skilled craftsmen who understood the aircraft intimately. The American approach, while requiring extensive documentation effort and standardized training programs, meant that maintenance could be performed by thousands of adequately trained mechanics rather than hundreds of highly skilled specialists. This scalability was crucial for operating thousands of aircraft across multiple theaters. The fuel system demonstrated yet another aspect of thoughtful design. The B-29 carried fuel in multiple self-sealing tanks distributed throughout the wings and fuselage. Self-sealing technology used multiple layers of rubber compounds that swelled when exposed to fuel, automatically plugging holes from small-caliber projectiles. The system wouldn't seal large holes from cannon shells or prevent catastrophic fires from direct hits on full tanks, but it significantly improved survivability against rifle-caliber fire. Japanese aircraft rarely featured self-sealing tanks because the technology added weight and reduced fuel capacity. The rubber layers took up space that could otherwise hold fuel. Japanese designers, obsessing over range and payload, typically sacrificed protection for performance. The Americans, with more powerful engines and stronger structures, could afford the weight penalty for improved crew survival. The philosophical difference was stark. Japanese designs optimized for maximum theoretical performance. American designs optimized for practical combat effectiveness with acceptable survivability. The oxygen system, though partially degraded by saltwater immersion, showed sophisticated engineering. High-pressure oxygen bottles fed regulators that supplied each crew station. The system automatically adjusted flow based on altitude, ensuring adequate oxygen at all times. Backup bottles provided emergency supply if primary systems failed. Japanese oxygen systems were simpler, often requiring manual adjustment by crew members who had to monitor their own oxygen supply continuously. The American automatic system reduced crew workload and prevented hypoxia accidents caused by improper manual adjustment. Throughout every system, Japanese engineers found this same pattern. American designs added complexity and weight to improve reliability, reduce crew workload, and enhance survivability. Japanese designs minimized complexity and weight to maximize raw performance. Neither approach was inherently wrong, but the operational results differed dramatically. By February 1945, as Japanese engineers continued their examination, American B-29s were conducting increasingly devastating raids against Japanese cities. General Curtis LeMay, who had assumed command of 21st Bomber Command in January, was revolutionizing bombing tactics. He ordered bombers to attack at night from low altitude, 5,000 to 8,000 feet instead of 30,000 feet. This negated the B-29's pressurization and high-altitude performance advantages, but drastically improved bombing accuracy and increased bomb load by reducing fuel requirements for climbing to altitude. The low-altitude tactics also reduced exposure to the jet stream winds at high altitude that had plagued earlier precision bombing attempts. LeMay's bombers carried incendiaries instead of high explosives, targeting the wooden construction of Japanese cities. The resulting firestorms devastated urban areas, killing tens of thousands, and destroying war production facilities dispersed throughout residential districts. The raids on Tokyo in March 1945 killed an estimated 100,000 people in a single night, more than either atomic bomb would later kill instantly. The engineers at Tachikawa could hear the bombers overhead, could see the flames consuming neighborhoods just miles away. They worked in the damaged hangar, studying the captured B-29 while its siblings rained destruction on their country. The irony wasn't lost on anyone. They were learning about technology their nation couldn't replicate, while that same technology was being used to systematically destroy Japan's capacity to wage war. The psychological impact on the engineering team was profound. These men had dedicated their careers to advancing Japanese aviation. Many had spent years designing and building aircraft they believed were world-class. The captured B-29 forced them to confront the reality that Japan had fallen behind, not just incrementally but by years. The gap wasn't merely in one system or component, but across every aspect: design philosophy, manufacturing quality, systems integration, crew training, maintenance procedures, operational doctrine. The Americans were simply ahead, and the margin was insurmountable given Japan's deteriorating industrial situation. Some engineers argued that Japan should attempt to copy specific systems, reverse engineering what they could from the captured aircraft. Others pointed out the futility of this approach. Japan lacked the industrial capacity to manufacture precision components in quantity. Raw materials were increasingly scarce as American submarines strangled maritime trade. Factories were being destroyed by bombing. Skilled workers were being drafted into the military or diverted to producing basic equipment like fighters. The resources needed to develop fire control computers or pressurization systems simply didn't exist. Any engineering effort devoted to replicating B-29 technology would divert resources from producing current fighters desperately needed to defend against those same bombers. The captured aircraft became a symbol of Japan's predicament. They could study their enemy's technology, could understand it in detail, but couldn't overcome the industrial and material deficit that was deciding the war. Knowledge without resources was merely frustrating enlightenment. The examination continued through spring 1945 as American forces captured Okinawa and the strategic bombing intensified. More B-29s were shot down or forced to crash land, providing additional specimens for study. The accumulating technical intelligence all pointed to the same conclusion. American aviation technology had surpassed Japanese capabilities across multiple domains, and the gap was widening. Japanese designers could still create elegant, high-performance aircraft when given adequate resources and time, but those conditions no longer existed. The engineers at Tachikawa compiled comprehensive technical reports documenting every system in the captured B-29. These reports circulated to military leadership, government officials, and senior engineers at major aircraft manufacturers. Everyone who read them understood the implications. Japan was fighting an enemy with superior technology, superior manufacturing capacity, superior logistics, and superior resources. The technical examination of the B-29 forced Japanese leadership to confront an uncomfortable truth. The war was unwinnable not because of tactics or strategy, but because of fundamental industrial and technological inferiority. The machines sitting in the Tachikawa hangar represented not just an aircraft, but an entire industrial civilization operating at a higher level than Japan could match. The technical reports from Tachikawa reached the desks of Japan's most senior military and political leaders by April 1945. Admiral Soemu Toyoda, chief of the Naval General Staff, read the findings with grim recognition. Vice Admiral Takejiro Onishi, architect of the kamikaze strategy, reviewed the documents and understood that desperation tactics stemmed partly from this technological gap. When conventional fighters couldn't reliably intercept heavily defended bombers, suicide attacks became a rational, if horrifying, alternative. General Yoshijiro Umezu, chief of the Army General Staff, absorbed the implications for ground defense of the home islands. If American bombers could systematically destroy Japanese cities and industrial facilities with impunity, how could Japan sustain resistance against an inevitable invasion? The captured B-29 provided concrete evidence for what many leaders had suspected. Japan was fighting an unwinnable war against an opponent whose industrial and technological capabilities had evolved beyond Japanese ability to counter. The fire control system particularly obsessed Japanese aviation engineers because it represented the future of aerial combat. Captain Minoru Genda, one of Japan's most brilliant tactical aviators and a key planner of the Pearl Harbor attack, was consulted on the implications of the automated defensive system. Genda understood immediately that this technology fundamentally altered bomber-fighter dynamics. Japanese fighter tactics had evolved throughout the war based on the assumption that bomber defensive fire required human gunners physically aiming weapons. Pilots learned approach angles that minimized exposure to defensive guns, attack patterns that exploited blind spots in coverage, and timing that took advantage of the slow traverse rates of manually aimed turrets. All of these tactics became obsolete against computer-controlled weapons that tracked smoothly, engaged multiple targets simultaneously, and calculated precise firing solutions regardless of approach angle. Genda's assessment was bleak. Japanese fighters lacked the performance to effectively engage B-29s equipped with this defensive system. The only viable tactic was mass attacks, accepting catastrophic losses, or suicide attacks that eliminated the need for survival. Japanese aircraft designers studying the reports began conceptualizing next-generation fighters optimized for bomber interception. Nakajima engineers proposed the Ki-87, a high-altitude interceptor powered by a turbocharged Ha-44 engine designed to reach 40,000 feet. Mitsubishi designed the J-8M Shusui, a rocket-powered interceptor based on the German Messerschmitt Me-163 that could climb rapidly to intercept altitude, then glide through bomber formations. Kawasaki developed plans for the Ki-102, mounting a 75mm cannon for standoff attacks beyond the range of bomber defensive fire. All of these designs remained conceptual or reached only prototype stage before the war ended. Japan no longer possessed the industrial capacity, raw materials, or time to develop and manufacture revolutionary new aircraft. The existing fighter force, flying Kawasaki Ki-61s, Nakajima Ki-84s, and Mitsubishi J-2Ms, would have to suffice for defense, despite their inadequacy against high-altitude B-29s. The captured bomber's pressurization system inspired Japanese engineers to reconsider environmental control systems for high-altitude operations. The Tachikawa Ki-77 experimental bomber program was revived briefly with plans to incorporate lessons learned from examining the B-29's pressurization. Engineers proposed a simplified system using a single pressure chamber for the three-man crew, avoiding the complexity of the American aircraft's multiple pressurized sections connected by tunnels. However, developmental work ceased in May 1945, when American firebombing destroyed the Tachikawa facility, killing several key engineers and destroying the captured B-29, along with all associated research equipment. The aircraft that had provided such valuable intelligence was reduced to twisted metal and ashes, victim of the very bombing campaign it had helped Japanese engineers understand but not counter. The psychological impact on Japanese aviators who learned about the B-29's capabilities through intelligence briefings was significant. Fighter pilots who had attacked B-29 formations reported that defensive fire was more accurate and intense than from any other bomber they'd encountered. Now they understood why. They weren't facing human gunners with limited fields of fire. They were facing a distributed weapons system that could engage multiple targets simultaneously with computer-calculated accuracy. The knowledge didn't make interception any easier, but it did explain the high casualty rates among intercepting fighters. Japanese bomber crews, flying obsolescent aircraft like the Mitsubishi G4M Betty or Nakajima B-6N carrier bomber, recognized that their aircraft offered none of the protection, comfort, or sophisticated systems American crews took for granted. They flew unpressurized, unheated aircraft with manual defensive weapons and minimal armor protection. Survival depended on avoiding interception rather than fighting through it, a luxury rarely available in the final year of the war. Some Japanese officers drew broader lessons from the captured aircraft beyond pure technical analysis. Colonel Takushiro Hattori, a staff officer involved in strategic planning, wrote a classified assessment arguing that the B-29 represented not just superior technology, but superior organizational capacity. He noted that developing such an aircraft required coordination between military planners who defined requirements, engineers who designed solutions, manufacturers who built components, assembly facilities that integrated everything, maintenance organizations that kept aircraft operational, and training establishments that produced competent crews. The entire system functioned smoothly only because America possessed deep expertise at every level, adequate resources to support development and production, and organizational structures that facilitated coordination. Japan, Hattori argued, lacked this systemic capability. Even if resources were unlimited, Japanese organizational culture, with its emphasis on individual excellence over systematic processes, would struggle to replicate the American achievement. The engine analysis produced particularly detailed reports. Japanese engine designers from Nakajima, Mitsubishi, and Kawasaki examined the Wright R3350 extensively. They marveled at the two-stage supercharging system that maintained power at high altitude. The first stage compressor forced air into a second stage, achieving compression ratios that Japanese engines couldn't match. The intercooler between stages cooled compressed air, increasing density and preventing detonation. The entire system was beautifully engineered, with every component optimized for its function. Japanese engineers understood the principles completely. They had studied supercharging theory, knew the thermodynamic equations, could calculate ideal compression ratios and intercooler sizing. But knowing and doing were different. Manufacturing the precision components required machine tools Japan didn't possess. The specialized steel alloys needed for turbine blades operating at extreme temperatures and rotational speeds weren't available in Japanese metallurgy. The fuel injection system required miniature precision components beyond Japanese manufacturing capability for mass production. Mitsubishi engineers attempted to design a comparable engine, designated the Ha-214, incorporating lessons from the R-3350 examination. The design featured two-stage supercharging, intercooling, and fuel injection. On paper, it would produce over 2,000 horsepower. Several prototypes were built and tested. They demonstrated promising performance initially, but suffered reliability problems that Japanese engineers couldn't solve with available resources. Bearings failed prematurely due to inadequate lubrication systems. Turbine blades cracked under thermal stress. Fuel injection systems clogged with impurities in lower-quality Japanese aviation gasoline. Each problem could theoretically be solved, but each solution required resources, time, and manufacturing capabilities that didn't exist. The Ha-214 program was abandoned in mid-1945 after consuming resources desperately needed for producing existing engines. The exercise demonstrated that understanding advanced technology and possessing the industrial base to implement it were entirely different challenges. The examination of the B-29's structure revealed American attention to manufacturability that Japanese designers often overlooked. Every component was designed not just for function but for mass production. Aluminum sheets were formed to shapes that could be stamped by presses rather than hand-formed. Assemblies used standardized fasteners available from multiple suppliers. Complex shapes were built up from simpler components that could be manufactured separately and joined, rather than machined from solid billets. The design philosophy prioritized production efficiency, accepting some weight penalty for ease of manufacturing. Japanese designs, often optimized for absolute performance, featured complex shapes that required skilled craftsmen to produce. A Japanese fighter wing might have slightly better aerodynamic performance than an American equivalent, but it took twice as long to build and required craftsmen who were increasingly unavailable as experienced workers died or were drafted. The American approach sacrificed theoretical perfection for practical producibility, achieving good performance from aircraft that could be built in enormous quantities by semi-skilled workers. The aluminum alloys used throughout the B-29 represented another technological gap. American metallurgists had developed alloys with superior strength-to-weight ratios through careful control of composition and heat treatment processes. The 24ST aluminum alloy used in many structural components offered excellent properties when properly heat-treated. Japanese metallurgists could analyze the composition through spectrographic analysis, identifying the precise percentages of alloying elements. But replicating the heat treatment processes that gave the alloy its properties proved difficult. American manufacturers used large furnaces with precise temperature control, controlled atmospheres to prevent oxidation, and carefully timed quenching procedures. Japanese facilities, often damaged by bombing and struggling with power shortages, couldn't consistently replicate these conditions. Even when Japanese engineers produced aluminum alloys with correct composition, the material properties often fell short of American standards due to processing inconsistencies. The quality control systems implied by the B-29's consistent manufacturing quality fascinated industrial engineers studying the aircraft. Every component showed evidence of statistical process control and systematic inspection. Dimensions were consistent within tight tolerances. Surface finishes were uniform. Assembly procedures had been followed precisely. This level of quality control required extensive measuring equipment, trained inspectors, documented procedures, and organizational commitment to standards. Japanese manufacturing, especially late in the war, struggled to maintain quality as experienced workers were lost and production pressure increased. Aircraft coming off assembly lines showed increasing variability in dimensions, finish quality, and assembly precision. This variability affected performance, with aircraft of nominally identical design performing differently due to manufacturing inconsistencies. American aircraft maintained consistent quality across thousands of units, suggesting manufacturing processes and quality control systems that Japanese industry hadn't implemented systematically. The navigation and bombing systems in the B-29 represented capabilities that would influence Japanese thinking about strategic warfare for decades after the war ended. The ability to navigate precisely across thousands of miles of ocean, locate targets in darkness or through clouds, and deliver bombs accurately from high altitude represented a revolution in strategic bombing. Japan had never developed comparable capabilities. Japanese strategic bombing doctrine, such as it existed, assumed visual navigation and bombing under favorable conditions. The idea that bombers could operate effectively at night, in weather, with electronic navigation and radar bombing, represented a paradigm shift that Japanese military thinking hadn't encompassed. Post-war Japanese military analysts would study these systems extensively as Japan rebuilt its defense forces under American guidance, but during the war, the capability gap was simply too wide to bridge. The crew training implications became clear as Japanese intelligence officers interrogated captured American aircrew. B-29 crews underwent months of specialized training before deploying to combat theaters. Pilots trained on the specific aircraft they would fly in combat, learning systems and procedures until operations became second nature. Navigator training included extensive instruction in celestial navigation, radio navigation, and radar operation. Bombardiers trained with the sophisticated Norden bombsight, learning to account for altitude, airspeed, wind, and target motion. Gunners trained extensively with the remote fire control system, learning to track targets smoothly and trust the computer to calculate. Firing solutions. Flight engineers studied every system in detail, learning to diagnose and repair problems in flight. Radio operators mastered multiple radio systems and communication procedures. Every crew member was a specialist, trained extensively in their specific role. Japanese bomber crews, by contrast, received far less specialized training. Chronic fuel shortages limited flight training hours. Complex systems training was minimal because Japanese bombers lacked complex systems requiring extensive instruction. Cross-training was common, with crew members expected to perform multiple roles. The training differential meant that American crews arrived at operational units far better prepared for the demands of combat than their Japanese counterparts. This training gap, like the technological gap, reflected deeper differences in national resources and priorities. America could afford to invest months training each crew member because the industrial base produced aircraft faster than trained crews became available. Japan, desperately short of both aircraft and fuel, couldn't afford extensive training even when instructors and facilities existed. By June 1945, as the examination of the captured B-29 neared completion, the strategic situation had become hopeless for Japan. American forces controlled Okinawa, placing invasion bases just 350 miles from the home islands. The naval blockade had strangled maritime trade, leaving Japan without oil, rubber, metals, or food imports. Strategic bombing had destroyed major cities and crippled war production. The Soviet Union was preparing to enter the war against Japan. Emperor Hirohito was being briefed on peace overtures through neutral intermediaries. The technical intelligence from the captured bomber, valuable as it was for understanding American capabilities, couldn't change the fundamental strategic reality. Japan lacked the resources to continue the war, regardless of how well they understood enemy technology. The final report on the B-29, completed in July 1945, ran to hundreds of pages of detailed technical analysis, supplemented by photographs, drawings, and component samples. Distribution was extremely limited due to the sensitive nature of the intelligence. Senior military officers, key government officials, and lead engineers at major manufacturers received copies. The report's conclusions were sobering. American aviation technology had surpassed Japanese capabilities across virtually every metric. The gaps were not incremental but substantial, representing years of development and industrial investment Japan couldn't match. Most critically, the report concluded that Japan lacked the resources and industrial capacity to close these gaps, even if the war continued for years. The captured B-29 had revealed not just advanced technology, but the vast industrial and organizational superiority that made American victory inevitable. When atomic bombs destroyed Hiroshima on August 6th and Nagasaki on August 9th, followed by Soviet invasion of Manchuria on August 9th, the Japanese government finally accepted the necessity of surrender. Emperor Hirohito announced Japan's capitulation on August 15, 1945. The engineers who had examined the captured B-29 understood that conventional bombing had already defeated Japan strategically. The atomic weapons merely provided a face-saving justification for surrender that had become inevitable months earlier. The fire control system they had studied with such fascination represented just one element of the comprehensive technological superiority that had made American victory unavoidable. In the post-war period, several Japanese engineers who had examined the captured B-29 during the war joined the newly formed Japan Defense Agency, applying lessons learned to help rebuild Japanese military aviation under American guidance. The experience of confronting superior technology and recognizing the industrial and organizational systems that enabled it influenced Japanese industrial development for decades. The story of Japanese engineers examining the captured B-29 represents more than technical intelligence gathering. It symbolizes the moment when a nation confronted the reality that its technological and industrial capabilities had been surpassed by margins too wide to overcome through determination or sacrifice alone. The engineers who spent months studying that aircraft learned lessons that extended far beyond fire control computers or pressurization systems. They learned that technological superiority stems from comprehensive industrial capability, systematic organizational processes, adequate resources, and time for development. They learned that understanding enemy technology and possessing the means to replicate it are entirely different challenges. Most painfully, they learned that their nation had fallen behind in the great technological race that would define the 20th century, and that catching up would require fundamental transformation of industrial and educational systems. The captured bomber sitting in the Tachikawa hangar had been more than an intelligence windfall. It had been a mirror reflecting uncomfortable truths about Japan's place in the modern industrial world, truths that no amount of courage or dedication could change. The fire control system that had so impressed those engineers represented not just sophisticated engineering, but an entire civilization's commitment to technological advancement, industrial capacity, and systematic problem-solving. Understanding that system meant understanding why Japan had lost the war before the first bomb fell. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.